It's an honor to be giving the first plenary talk of this year's ICCAS meeting. Today, I'll share my perspectives on the design of wearable robots for physical and human-robot interaction. Today, we see robots increasingly sharing the physical environment with humans. Robots help us with tasks in our homes. They are used to deliver rehabilitation, and surgeons use robotic systems to perform specialized procedures. In each of these applications, the human and the robot are physically coupled and interacting to complete tasks. Wearable robotic devices are an especially challenging research topic within the area of physical human-robot interaction, because the robotic device and the human must coordinate their movements, intentions, and physical interactions in intricate ways. Here are three applications of wearable robotic devices. An exoskeleton might be used to assist an individual who has lost function due to neurological injury, such as stroke. In the workplace, exoskeletons are being used to protect workers from injury. We could even envision a wearable robot that enhances normal function. We all dream of having an Iron Man suit, right? These are all applications of physical human-robot interaction, and they necessitate that the human and the machine are linked physically. Think about how the robot fits the body, that they share knowledge of each other's intentions, and that they are working in concert to achieve a common movement goal. A major focus of research in my lab has been in the development of exoskeletal robots for upper limb rehabilitation. We have explored how we can use robotic devices to restore function following neurological injury, such as stroke or spinal cord injury. Here are a number of systems that we have developed for such applications. Our contributions have ranged from design of novel hardware systems to control design to methods for detecting movement intent. Let me provide some context for robotic rehabilitation. In general, rehabilitation following neurological injury, like a stroke or injury to the spinal cord, is centered on the concept of neuroplasticity, or the ability of the nervous system to change and reorganize itself. This critical finding, that damage to the nervous system is reversible, led to a major shift in rehabilitation practice. This was a shift from mitigating the effects of the impairment, such as learning to compensate for the loss of motion or learning to use movement aids like walkers, to actual active therapy, which can induce neuroplasticity and lead to recovery of function. Active therapy has been shown to be most effective when the patient is actively engaged in that intensive therapy. Robotic devices are well suited to provide intensive rehabilitation. They are ideal for repetitive, high-intensity therapy. And another added benefit is that the onboard sensors of the robot allow for quantification of therapy outcomes in ways that were not achievable with traditional rehabilitation. My group is not alone in developing exoskeletons for rehabilitation. A number of advanced multi-degree of freedom exoskeletons have been designed for this purpose. Here's some you might be familiar with. My lab's Mahi Exo 2 is a 4-degree of freedom robot that supports elbow, forearm, and wrist movements. The Armeo Power is a commercially available rehab exoskeleton that focuses on shoulder, elbow, and wrist movements. The Harmony exoskeleton, developed in Ashish Deshpande's lab at UT Austin, and the Cadence 7, developed by Jacob Rosen of UCLA, are bimanual exoskeletons that support shoulder, elbow, and wrist movements. These devices share a number of characteristics. They all have a grounded base, rigid linkages, and complex kinematic mechanisms and transmissions. Why do they share these characteristics? Well, for rehabilitation or movement assistance, we require sufficient torques to overcome gravity and to support movements throughout the upper limb's full range of motion. We must ensure appropriate alignment of the robot joints and the human joints, while still allowing for adjustability and customization of fit to an individual. And we must obtain accurate measurement of the limb pose so that our control algorithms can impart appropriate assistive forces. For robotic devices intended to be rehabilitation aids for clinic-based therapy, these large grounded devices are appropriate. In fact, many rehabilitation gyms and clinics have devices like these next to treadmills and stationary bikes. They're just another tool for delivering therapy to patients. This approach to the design of wearable robots is not compatible with the vision of robotic devices that are all-day wearable, maybe even under clothing. On the left is a concept drawing from the Harvard Biodesign Lab headed by Professor Connor Walsh. They have been using designed textiles, artificial tendons, and a few carefully placed actuators to provide movement assistance and support for aging populations and for load-carrying applications. A similar soft robotics approach has been taken by Professor Lorenzo Marcia at Heidelberg University. He is developing compliant exosuits to support upper limb movements. Similarly, Professor Kujin Cho from Seoul National University has developed assistive soft exogloves. Again, the combination of soft materials and tendons allows the application of assistive forces to enable grasping. These soft wearable robots augment the capabilities of healthy individuals by promoting improved movement efficiency and can assist those with muscle weakness or patients who suffer physical or neurological disorders. Compared to the traditional rigid exoskeletons that I showed on the previous slide, these systems have several advantages. The user's joints are unconstrained by external rigid structures. The suit itself is rather light, though some require remote power or actuation modules. The result is an exosuit that minimizes unintentional interference with the body's natural biomechanics. Still, inherent limitations exist with a fully soft approach. The devices usually support specific movement patterns. For the grasping application, the tendons are actuated, causing the hand to assume a power grasp. The Aries Lab exosuit shown here in the middle supports only elbow flexion and extension. And typically the lower limb exosuits provide assistance at one specific point in the walking gait cycle. Another limitation of fully soft exosuits is the amount of assistance that can be provided. Given their compliant nature, these systems typically lack anchor points at which significant loads can be applied to the wearer. Finally, soft robotic systems are often not able to measure the orientation of the limbs with the same precision as the rigid linkages of traditional exoskeletons. This limits the precision with which assistive forces can be applied to achieve dexterous or precision movements. To address the limitations of both fully rigid exoskeletons and soft robotic exosuits, my lab has been collaborating with NASA's Wearable Robotics Lab at NASA's Johnson Space Center to develop what we call hybrid wearable exosuits. Today, I'll share a bit of information about two such projects: Armstrong, a system for support of upper limb movements, and Spar Glove for improving dexterity and grip strength. We are using a hybrid rigid soft approach. With this approach, we can achieve high torques necessary for movement assistance. We can improve comfort and wearability with soft goods compared to fully rigid systems, and we can promote the portability achieved via remotely located actuators. These devices support movements necessary to achieve activities of daily living. They can provide therapeutic interventions for rehabilitation applications, and they can also assist movements of individuals who may not be able to recover independent function on their own. The Armstrong device shown here is the first portable soft wearable robotic device to be tested on individuals with traumatic brain injury, or TBI. And it demonstrates the capability to adequately actuate the shoulder of an impaired individual in flexion and abduction. These movements in particular are important for providing functional range of motion in the TBI population. Typical movements that capture functional workspace include the hand at the ear, the hand over the chest, and reaching out to a work surface. All of these include some level of proximal upper extremity movement, including shoulder flexion and abduction, and elbow flexion and extension. In our recent publications noted here, we showed that through actuation of the tendons, we could constrain movements and support the individual in completing elbow flexion and extension movements without compensatory shoulder flexion extension or abduction adduction. Other potential applications of Armstrong could be human augmentation or resistive exercise systems to counteract microgravity effects. I'll go into more detail now regarding our second collaborative project with the Wearable Robotics Lab at Johnson Space Center, the development of the Spar Glove. The Wearable Robotics Lab has significant experience designing assistive gloves for simple power grasp functions. For example, the RoboGlove shown here can apply 15 pounds of grip force in a power grasp pose. As I alluded to earlier, the spectrum of wearable devices includes a gap in the rigid-soft spectrum of device design, namely this hybrid space in which we're working. A hybrid device stands to leverage the ability to provide high torque outputs typical of rigid devices, combined with the compliant ergonomic interfaces of soft devices. This can enable improved functional movements of the hand beyond the capabilities of existing devices. The Spar Glove is a novel design integrating rigid and soft elements to overcome design limitations of fully soft or fully rigid devices. The key contributions of this design can be organized into the design of soft goods, power transmission, and compliance sensing. The soft goods design was based on a commercially available glove to leverage low-cost, refined designs and materials where practical. The glove base is made out of a combination of lycra elastic materials and simulated microsuede for comfort and grip. The palm strap, similar to how a boxer wraps their hand before sparring, serves as the main method of fastening the soft goods to the hand of the wearer. The strap is tightened with a BOA fastener, a commercially available ratcheting closure device found on equipment such as snow boots, where the user has reduced dexterity from wearing gloves. By removing the need for Velcro, buckles, or other fastening mechanisms, this glove can be securely fastened and unfastened to the hand by users with limited hand function. The glove features a Bowden cable transmission that terminates in the palm strap, reducing the fit and stiffness requirements on the soft goods and ensuring a strong and comfortable interface with the wearer. Instead of requiring the glove to distribute the conduit reaction loads, an ergonomically curved palm bar is sewn into a sleeve in the palm strap using holes located at the ends of the palm bar. The shape is based on the retaining bar used to prevent spacesuit gloves from deforming when pressurized. The palm bar was 3D printed out of 316 stainless steel using selective laser sintering to facilitate greater resolution in sizing and to accommodate curved tendon paths for the thumb degrees of freedom of the glove. The bases of a series of vertebrae-like links designed to prevent finger hyperextension also are anchored to the palm strap and serve as a termination point for the Bowden cable transmission. This video shows some of the grasping poses that are achievable with the Spar Glove. The various degrees of freedom that enable finger flexion and extension and thumb motion are independently controllable, but we've illustrated these poses that are known to be necessary for achieving activities of daily living and functional independence of our participants. We compared the capability of our Spar Glove to the Graspy Glove by Popov. Popov proposed a metric based on weight, bidirectional capability, dexterity, and force. Based on this metric, the Spar Glove outperforms the state of the art. The table includes specific capabilities of the glove in terms of range of motion, grasp force, achievable poses, and compares these to two other glove designs and the requirements for activities of daily living. Our hybrid rigid and soft approach to designing wearable robotic devices for the upper limb and hand achieved a few key goals. One, we're able to transmit higher forces and torques to the limb than fully soft devices, expanding the range of applications that these devices can be used for. We have also demonstrated that this approach can facilitate complex multi-degree of freedom movements. Armstrong in particular supports 3 degrees of freedom of the upper limb, while the Spar Glove assists flexion and extension and can assist multiple grasping poses. Still, there are remaining challenges that we have not fully addressed with this approach. These hybrid wearable robotic systems are still very compliant, That means the device can move relative to the limb, making accurate, reliable, and repeatable sensing of joint angles and limb poses challenging. This directly affects the performance of any control algorithm that one would implement. Second, the integrated rigid elements that are used to transmit loads still move relative to the user's body, meaning that the point of application of forces can vary across subjects, or even as the user moves their own limbs. Third, our Bowden cable actuation scheme can transmit high forces, but it's subject to frictional losses and binding, making it less reliable than other actuation methods. And finally, we are just starting to explore intuitive control schemes that recognize user intent and allow these devices to work fluidly with the wearer. Detecting the user's intent to move is important for devices like Armstrong and the SPAR glove that can assist movements, and it's also important for rehabilitation applications where we want to ensure that the user is actively engaged in their therapy. So at what level should we detect the intent to move? We can think about detecting the movement directly using an impedance type control scheme, perhaps measuring the forces and torques applied at the physical interface between the human and the robot. We might also consider detecting intent from the user's method of actuation, using electromyography or EMG sensors applied to the surface of the skin to measure the muscle activation. We can also consider measuring the plan through electroencephalography. This would allow us to detect at a very high level the intended movements that the user might be interested in making. I'm going to focus today on EMG, and EMG offers a few benefits. One, it gives us access to more impaired populations. I'll get to this in a minute. Second, it can be used to prevent compensatory movements because you can use EMG to detect the specific activation patterns of specific muscles that you want to see the user engaging to achieve a movement. And EMG is relatively non-invasive and quick to set up compared to other methods like brain-machine interfaces. Still, challenges exist in modeling the force to surface EMG relationship. So again, we can think about measuring intent through movement directly using impedance control techniques. We can measure actuation via electromyography. We can measure the plan via electroencephalography. And these benefits, we really think kind of lie in the middle here, where we're getting lower level information than the plan, but we're able to enforce specific movement patterns by looking at the patterns of muscle activation. The further you move towards the robot, the more distal the source of the control signal. So for applications of rehabilitation, we want the patient to be maximally engaged in their rehabilitation therapy. Therefore, the robot must learn to work with the human, adjusting the contribution of the robot in response to varying capabilities of the participant. To achieve this, we developed a subject adaptive controller that balances assistance and challenge. First, we model the subject's input and then provide only as much assistance as is needed to complete the desired trajectory. We then vary the challenge of the task by regulating the allowable error and by recalculating the allocated time for task completion based on performance. Now, in this implementation, we are measuring the motion of the user. So we're at that impedance control implementation level. We require the individual to have some capability to generate movements so that we can determine what they're able to contribute to a movement and what the robot needs to provide as supplemental assistance. Here's a block diagram of the subject adaptive controller that we have implemented in our work. We define a desired trajectory of the exoskeleton indicated with the green block. There are two inputs, the user's contributed torques and the control action torques, and together these result in some motion of the robot. Blocks with a yellow background include components of the adaptive controller proposed by Slotin and Lee that is used to estimate the action required of the robot. The feed forward action is a model of the person's capability. If there are errors in the estimation, those will be acted upon by the feedback portion of the controller, and the adaptation law will refine the model of the feed forward action expected of the user. The blue block is the challenge aspect of the controller, where the allowable feedback gain is modified, making it easier or harder for the user to track the desired trajectory. The dashed line from the feedback gain modification block to the feedback action block refers to a discontinuous update of signal variables. In other words, the feedback gain is changed on a task-by-task basis, not within a particular trajectory following the trial. Here we show an example video of a person. Let's see if I can get this to run. Here we show an example video of a person using the exoskeleton in the adaptive control mode. At first, the subject is doing nothing, and the robot is assisting in the completion of the movements. You can see the subject position, what I'll refer to as the donut, lagging behind the ghost cursor, the white ball, which is following the defined ideal trajectory. Now you see that the subject is driving the robot's movement and is leading the ghost cursor and is therefore ahead of the desired trajectory. After the subject leads the ghost cursor for 2 consecutive center out, out center movements, the ghost cursor disappears and the controller now allows the subject to define the trajectory. This work was completed by 2 former PhD students in my group, Uku Palavan and Dylan Losi. Let's look at how the control behavior changes with different user behavior. In this plot on the left, you can see that the feedback gain plotted on the y-axis changes versus time based on whether the user is passive, left of the black bar over here, or active to the right of the black bar. When the user is active, the feedback gain decreases, meaning that there is less corrective action of the robot to track the trajectory. It is possible to measure the engagement of the user. Based on surface EMG measurements, we determined how active the participant was with and without the subject adaptive controller active. The involvement time, T involved, was calculated as the amount of time the RMS value of the EMG data was larger than a threshold of the maximum voluntary contraction recorded on a particular session. We windowed this over 50-second time periods in a session, and this is data here on the right from a single subject pilot study. You can see that throughout the experiment, the activity of the participant is greater, shown with blue bars, when the adaptation algorithm is active, compared to the red bars when the adaptation algorithm is inactive. We have clinically evaluated the performance of these different controllers. Let me get this video to play as well. We've evaluated the efficacy of these control modes for rehabilitation of individuals with spinal cord injury. These videos show the difference in dexterity and coordination of our participant at baseline, that's the video on the left, compared to post-treatment after a 4-week-long rehabilitation protocol, and that's the video on the right. As you can see, the individual was able to complete the 9-hole peg test much more efficiently with better movement coordination. Details of our clinical findings were published in the Frontiers in Neurorobotics, and I would point you to that for details of the clinical studies. Just as we used EMG in the last slide to measure the engagement of participants during rehabilitation with our upper limb exoskeleton, we can also use EMG for intent detection and control. The work that I'm going to describe next was carried out by my recent PhD student, Craig McDonald, and master student, Troy Dennis. Intent detection based on kinematic data, like we used in our subject adaptive controller, leaves out more impaired subjects who may not be able to initiate movement on their own. It also may not be suitable for compliant wearable devices, where we don't have precise measurement of limb position. Electromyography, or EMG, gives access to muscle activation, leveraging the existing neuromuscular control system. EMG signals have been observed in paralyzed limbs of individuals with spinal cord injury, but there are a number of challenges with this approach. The most notable challenges are noise and crosstalk between the different EMG channels. The EMG activity is highly subject and session specific, can change over time, And these challenges are magnified for our impaired population. The EMG signal itself is random and complex. So one way that we can work with this data source is to extract features from the signals. Two commonly used features are the root mean square and mean absolute value of the raw EMG signal. Both of these, RMS and MAV, are analogous to amplitude of the signal. Other features of the EMG signal are analogous to frequency, including waveform length, zero crossings, slope sign changes, and autoregressive coefficients. When we want to use EMG as a way of detecting user intent or as a control input, there are two common approaches that are taken. One is direct mapping, where one pair of antagonist muscles corresponds to one motion with varying levels of torque output based directly on the amplitude of the EMG signal. An alternative approach is to use pattern recognition methods. Here, all muscles of, for example, the upper limb are considered to investigate repetitive patterns of muscle activations. This allows us to capture more information. It's also more anatomically correct since multiple muscles can contribute to movements, not just a pre-selected pair of antagonist muscles. This also allows us to decode patterns for multi-joint or multi-degree of freedom movements. We asked participants to complete a target hitting task using the MAHI XO2. The task required them to make isometric contractions while the exoskeleton was controlled to hold a neutral position. The contractions would be those required to generate motion towards different targets visible on a computer screen. Participants performed both single and multi-degree of freedom target hitting tasks. Here you can see illustrations of the single degree of freedom movements, elbow flexion extension and forearm pronation supination. Elbow on the left and forearm pronation supination on the right. These were then combined into multi-degree of freedom movements of the proximal upper limb. On the right, you can see illustrations of single degree of free movements of the wrist, radial ulnar deviation, and wrist flexion extension. Again, these were combined into multi-degree of freedom movements of the distal upper limb, specifically the wrist. In the experiment, the user is held in a neutral position by the exoskeleton as they attempt to generate movement about the selected degrees of freedom. They received commands from the visual interface to instruct them on what to do. And for each mode, targets were presented in a random order with the user generating an isometric contraction during an active phase and then relaxing their muscles during a rest phase. Once the threshold for detection of myoelectric activity is set during the calibration step, the training data is collected in the manner depicted here for the necessary number of trials, and a classifier is fit to the training data. Then predictions made by the classifier are tested also in the manner depicted here. In other words, it's the same as the collection of training data from a user's perspective. Finally, the classifier predictions are tested with the robot carrying the user to the predicted target and back after the active phase of each trial. We examined if we could detect whether the user was at rest or attempting motion. Then we determined which parts of the EMG signal contained the most useful information, those features that we wanted to extract from the signal. And finally, we evaluated classification performance to see if we could tell which direction the user was attempting to move and how reliably we could determine those directions. Here are confusion matrices averaged across all 10 of our able-bodied participants, showing online classification performance with corrected regularization. Each of the 4 single degree of freedom across the top and 2 multi-degree of freedom modes correspond to a 2x2 or 4x4 confusion matrix. Here you can see the classification of elbow flexion versus elbow extension, forearm pronation versus forearm supination, wrist flexion versus wrist extension, and wrist radial ulnar versus wrist radial versus wrist ulnar deviation. And then here's the 4x4 for those 2 degree of freedom movements, either elbow combined with forearm or the 2 degree of freedom wrist movements. We see very good classifier performance for our able-bodied single degree of freedom movements. And we also see strong performance as well for our multi-degree of freedom movements. 4 individuals with spinal cord injury also completed the study. You can see that they range in age and level of spinal cord injury and the severity of injury. Again, the confusion matrices are averaged across all participants, showing online classification performance. Again, we see fairly good classifier performance for single degree of freedom movements in our spinal cord injured population, but we see deteriorated performance when classifying multi-degree of freedom movements made by individuals with spinal cord injury. Here we examine which features were most often selected by our recursive feature elimination with cross-validation method across all participants, both able-bodied and those with spinal cord injury, and across all 8 EMG channels, averaged across single degree of freedom and multi-degree of freedom modes separately. The black bars show the standard deviations. So the light bars are single degree of freedom results and the darker purple bars are multi-degree of freedom results. We're plotting the frequency that each feature was selected versus each of the individual features that we explored. These features include root mean square, mean absolute value, waveform length, number of zero crossings, number of slope sign changes, and then 4 different coefficients from our autoregressive correlation. As you can see, the root mean square and mean absolute values had a higher average selection rate greater than 50% in both single and multi-degree of freedom modes, meaning that it's the amplitude of the EMG signal that's most informing the classifier as opposed to the frequency-based characteristics that I showed earlier. These 2 plots summarize our classification accuracy, and they're separated into averages of single degree of freedom modes on the left and multi-degree of freedom modes on the right for our different methods of feature selection and classification. Here we were interested if our recursive methods that use a subset of data would be as accurate as classification techniques that use the full set of features and have more computational demands. For each subgroup of 3 bars, the methods used to generate the data from left to right are the recursive feature elimination with cross-validation, that's our method, the first bar, all features using all possible features from all channels, and RMS using only the root mean square value of each channel. The first grouping of 3 bars in red shows the average scores across all able-bodied participants, and the remaining 4 groups show the scores of individuals with spinal cord injury, because there's quite a bit of variability in the performance depending on our participants. Our results show that the recursive feature elimination with cross-validation performs nearly as well as using all features, with significant computational gains. So key findings. I've presented recent results on the design of a myoelectric control interface for an upper limb exoskeleton, which we evaluated with able-bodied and spinal cord injured individuals. The system was able to classify intended movement direction with a high degree of accuracy for our able-bodied users across both single and multi-degree of freedom modes, while the classification performance was more variable with our spinal cord injured users. Still, we achieved high accuracy with some frequency across control modes. The use of EMG to control an exoskeleton in real time shows some promise for translation from the unimpaired population to our target population of spinal cord injury, particularly with simpler single degree of freedom directional classification tasks. And such methods are likely transferable to the applications of wearable robotic devices that I presented earlier in the talk, in order to improve the intuitive control of assistive devices such as Armstrong or the SPAR glove. So today I've shared some of the challenges and opportunities in designing and controlling wearable robots for physical human-robot interaction. In the case of assistive robots like SPAR glove and Armstrong, the challenges are really twofold, both in the design and in the control. From a design aspect, we have these compliant devices that are worn on the body. The soft devices give us the wearability aspects that we want, but they are unable to impart large forces and torques, meaning that they're limited in how much they can be used for assisting movements of significantly impaired individuals with stroke and spinal cord injury. Another challenge of the compliant aspect of the device is the resolution and precision with which we can sense the limb positions. As we all know, our control algorithm performance depends on quality data to drive our control behavior. And so when our precision of sensing limb position is impacted by the flexibility and softness of the wearable device, that's going to directly impact our closed loop control performance. Another challenge is that these devices move relative to the body. Rigid exoskeletons allow us to precisely fit the person into the robot, measure those joint angles, and control a rigid device in a very predictable and repeatable way. But when our wearable devices are moving relative to the skin and we don't have precise measurements of position, now we also are not imparting the forces on the same repeatable location on the limb, performance is going to degrade. A final challenge with these wearable soft compliant devices is understanding the intent of the user. Because again, we don't have reliable kinematic information about the device, we need to rely on other aspects to measure that intent. And so I shifted to talk about our work in rehabilitation, where we've been using EMG as a method of intent detection. I started by talking about applications of the MAHI Exo 2, where we detected intent by measuring movement. With a rigid exoskeleton, this works quite well. I can use a feed-forward adaptive control algorithm implementation. I can use the error between the expected and the desired motions to update my model of the user contribution to movement. And I can vary the challenge by adapting the feedback gains to allow more error or less error, giving the user more challenge in tracking that trajectory. But this implementation of our subject adaptive controller, again, relies on measuring kinematics. That's something we can do really well with a rigid exoskeleton, but as we translate these findings to a more wearable soft compliance system, we're going to face challenges, again, in the precision with which we can measure those limb kinematics. So I introduced a method that we've been using in our rehabilitation applications to detect movement intent using EMG. Here we use surface EMG electrodes over the muscles of the upper limb. We use an 8-channel system, and we are looking at different classification algorithms, understanding which features of that EMG signal are most important for detecting movement intent, that we can do reliably and quickly in an online method that can be used for controlling these assistive and rehabilitation devices. The challenges with EMG as a signal source, though, are not small, right? So we have issues with the repeatability of the signal itself, of noise and crosstalk in the signals, and high variability even across a single user, even within a single session. So we need ways to quickly calibrate and then classify these EMG signals. And so using recursive feature elimination methods that use a subset of the important features of the EMG signal have shown to be a fairly reliable way of detecting movement intent. For able-bodied individuals, we're able to do this for both single and multi-degree of freedom movements. And in our spinal cord injured population, we're seeing pretty good performance with single degree of freedom movement classification of the upper limb, but challenges still exist in classifying multi-degree of freedom movement intent. So no shortage of work for us to do in improving the performance of wearable robotic devices, both on a mechanical design standpoint and from a control implementation standpoint. I hope that this talk has inspired you to develop innovative solutions to the challenges that I've described. I have appreciated your attention to my talk, and I look forward to your questions during the Q&A. Thank you.